Good day. This is the sixth in a series of videos designed to explain how to create predictive models which are simultaneously explicable and precise. So for those of you playing the home game, recall that last time the thing about which we spoke was how to create groups of increasing target variable, whatever that would be in your particular case. And these groups came from grouping together observations that were sorted by creating machine learning models, in particular those that came from an XGBoost model and a random forest model. Now, if you're paying attention, a question should have occurred to you, and that question is, hey, wait a minute, from whence came those models? What exactly is going on there? How did you come up with the parameters for those things? And that's a reasonable question, and that's the question that we are going to address in this particular video. Now, we're going to talk through maximum likelihood estimation, then we're going to talk through least squares, and then we're going to see their practical differences. But the important thing to keep in mind is that these things, of course, are not coming out of the ether. So you start off with, say, just your basic linear model. You've got your conditioning y on x, and that's apparently equal to a plus xb. And a reasonable question is, well, where does a and b, where do those coefficients or those numbers, from whence do they come? Or, here's a more complicated model where you are still regressing against a single variable, but now we've got 5 parameters involves a, b, c, d, and e. So from whence are those variables coming? And so that is a question, again, related to the random forest and the XGBoost stuff that we did last time, because those models, among other things that they're doing, and this is not meant to be a lecture on those modeling techniques, there's plenty of resources for that, but they are coming up with these kinds of numbers here. They are coming up with these A's and B's and D's here, not so much the C's and E's, but that's for other reasons. Where are they coming from? What's going on there? And the answer is, well, there's a few different methods that you can employ to get these numbers, to generate them. And if you examine the code that I used for both the XGBoost and the random forest, what you'll discover is that, in fact, what I was doing was I was minimizing the sum of squared errors, and we'll discuss why subsequently. So the first thing that we are going to discuss is maximum likelihood estimation. And so now, why are we discussing this? Well, among other things, this is the method that's typically used in a lot of the software statistical packages that you would use on some sort of regular basis. So SAS uses this, for instance, and I recommend that if you really want to get into the guts of some of this stuff, look at their documentation for their HP Gen Select routine. R uses this as indicated in the documentation for the GLM function. Python uses this as indicated in the stats models documentation. So here's how this works, is what you do is you say to yourself, okay, I'm going to hope that the conditional distribution of my target variable y with respect to x has some density with respect to some dominating measure, and then what I'm going to do is I'm going to use the density that comes from that and maximum likelihood estimation to estimate these parameters here. And so typical distributions, and these are the ones we'll explore in the R code section of this presentation, typical distributions are Bernoulli, normal, Poisson, gamma, and Tweedy. Now, before proceeding, again, I want to say this lecture is not going to be one that has to do with maximum likelihood estimation. Again, there's plenty of material covering that. What we're going to be discussing here is how this works in practice and what practical considerations are, as opposed to developing some sort of theoretical underpinning. But what's interesting, though, is when you're thinking about the theoretical underpinning, is to realize that it really came into being somewhat gradually. And so, for instance, who was it? It was Stigler wrote he wrote a paper called The Epic Story of Maximum Likelihood. So this technique's been around for a while. This quote here is a very interesting one because this was written by Ronald Fisher in his 1922 paper dealing with maximum likelihood estimation. And he writes, "Such a method," referring to maximum likelihood, "I believe provided by the method of maximum likelihood, although I am not satisfied as to the mathematical rigor of any proof which I can put forward to that effect. Readers of the ensuing pages are invited to form their own opinion as to the possibility of the method of maximum likelihood, leading in any case to an insufficient statistic. For my own part, I should gladly have withheld publication until a rigorously complete proof could have been formulated, but the number and variety of results which the method discloses press for publication, and at the same time I am not insensible to the advantage which accrues to applied mathematics from the cooperation of the pure mathematician, and this cooperation is not infrequently called forth by the very imperfections of writers on applied mathematics." So quite the swipe at applied mathematicians and statisticians by Ronald Fisher there. And to his point, he does not provide proof, mathematical proof, of the properties of maximum likelihood estimators in that paper. That doesn't come until Wald. Wald assumes absolute continuity with respect to Lebesgue or counting measure in 1949, and then proves various and sundry things about it. If you are interested in some worked examples, I recommend checking out Casella and Berger in their Statistical Inference book. Okay, but like I said, that's all the theory stuff. That's the stuff of textbooks. What we want to discuss is how this looks in practice. So a reasonable question, and one that you should consider at the start of all of these sorts of operations, is how will I know? So maximum likelihood estimation only works if the conditional distribution of your target variable with respect to your predictor variables takes certain is of a certain type of distribution. So how will I know? So let's talk about the first one, Bernoulli. How will I know? And the answer is, well, in this case, your probability mass function is this, where x is your response variable. And in this case, we're in really good shape. This is a very easy one. How will you know? Well, you know if your outcome is either 0 or 1, true or false, this or that. If that's the case, your distribution is a Bernoulli distribution. So that's fairly straightforward. And you can proceed with maximum likelihood estimation. Now we move on. Normal. How will I know that my data actually, the conditional distribution follows a normal distribution? Well, the density looks like this. And you go, yes, of course, I'm very comfortable with those numbers. I see them all the time. And the density curves look like this. But again, how will you know that the conditional distribution is normal, is required? And so some of the text that you'll read will say, well, you should do things like plot your data, exploratory data analysis, EDA as it's sometimes called, get a sense of, do a histogram, get a sense of what the distribution of those is. And so you go, oh okay. So I generated a data set and put it into deciles and looked at it, and it looks like this. And you go, oh, it looks like a uniform random variable. I guess we cannot use maximum likelihood estimation here with a normal distribution. Oh, wait. It turns out that if you do the centiles as opposed to the deciles, all of a sudden it looks like we have clusters of normal distributions. Well, isn't that nice? Maybe we can have some sort of categorical variable here such that when you regress against it, the conditional distribution is normal. So this is a bit troubling, of course, because the data set that I generated to produce this example, on the one hand, looks uniform. If you look at it differently, it looks like there's pockets of normality, clusters of normality. But the data set that I used to create this example had 100,000 observations in it, and so if you graph a histogram with 100,000 observations, you're just going to get a straight line. So that's not helpful. So how do you actually know? And the answer is it can't come simply from considerations of, oh, I plotted it this way and I plotted my target variable and it looked this way. Because we're not interested in the distribution of the target variable. We are interested in the conditional distribution of the target variable. So creating a histogram of your target variable to discover an underlying conditional distribution is insufficient, and that is the point of this. So then how could you know? Well, among other things, what is the case is that there is more than one central limit theorem. There are actually central limit theorems. And the central limit theorems, as you go further and further out into abstraction, basically what they're doing is they're trying to get to the conclusion of the central limit theorem, namely that the sample mean is normally distributed, but by assuming less and less stuff. And so one of them comes to us from Lindeberg and Feller, and it basically says, look, if you assume that your target variable can be thought of as the sum of independent amounts being accumulated, the sum of independent amounts, then your target variable is asymptotically normal. So that's one way to think about when you can assume that the conditional distribution of something is normal. Okay, well, what about a Poisson random variable? Again, we go, well, here's your mass function, and you go, of what does that remind me? Oh, hey, isn't that just the expansion for e to the lambda? And you go, yes, in fact, it is. And then you might say to yourself, well, that's interesting. Can't I simply take any non-negative sequence of real numbers that sum to 1 and say, hey, this is a distribution on on the naturals or some countable set? And the answer is, yes, you can. And so then you might say to yourself, well, then why did you pick this one? of all the infinite sums to consider, why did you select this one? And the answer is as follows. So very briefly, this mass function gives rise to these kinds of graphs. So here's one way to think about things to determine whether or not you might be dealing with a Poisson random variable. And this comes to us from Erhan Schindler's Introduction to Stochastic Processes. Originally came out in 1975, now available in Dover publications since 2013 for a paltry sum. I highly recommend you obtain it. It's a very well written book. And here's the thing, is that although the Poisson random variable has kind of an odd formula, you can actually describe a Poisson variable in very qualitative terms. And there are 3 of them, and here they are. One is that it's a counting variable. And so what you do is you basically say, look, I'm going to assume that my events occur one at a time. So you can think of customers coming up to a cash register, for instance. They come one at a time. 2, the number of events in an interval of time has nothing to do with what happened before that time. So the number of customers coming in between 10 and 11 has nothing to do with the number of customers coming in between 9 and 10. Now you might say, but they are related. And my answer is, great, then it's not Poisson. This only works in this case. And finally, that the number of events in intervals of equal length have the same distribution. And so if you say, what's the count of customers coming in between 9 and 10 versus 10 and 11, the distribution of those 2 random variables is the same. Well, in that case, you can assume that the number of events in an interval of time is Poisson with mean proportional to the length of the interval. Okay. So now, continuing with this guy, we can talk about the gamma distribution, and it looks like this, and you go, what on earth is that? And the answer is, that's the gamma function right there, hence the gamma distribution. The gamma function is basically a continuation of the factorial function. That's one way to think about it. In this, of course, right here, these 2 terms, or 2 factors here, this is what you integrate to obtain from 0 to infinity to get the gamma function. So the PDFs look like this, and you go, again, how will I know this is really wacky looking? Yeah, it might be wacky looking, but one of the nice things about the gamma function is that you are able to play around with the relationship between the mean and the variance. So how will I know that this is the thing I should be using? And the answer is, well, at least in one case, we know that going back to the Poisson process from the previous slide, if instead of thinking about the number of arrivals in any interval of time, you instead think about, well, when is the time of the nth arrival going to take place? It turns out that question, when does the 100th customer come in, that distribution is a gamma distribution. And so the gamma distribution is the distribution which generalizes the distribution which is the answer to this question. Now, before proceeding to the next slide, we should note a few things from antiquity. And one is that the gamma distribution is used a lot in insurance applications, in particular the severity of different claims. Why is that? Well, as far as I can tell, Charles Hewitt back in 1979 was the first one to apply a gamma distribution to try to model the severity model claim severity. So that is to say, how many dollars lost when cars collide and that sort of thing. And he had previously in 1966 and 67 used it to model the distribution of the size of premium as well as loss ratio distribution. So I guess he had a hammer and everything looked like a nail. Now, why do I mention that? Well, it's because that leads us into the next distribution, which is the Tweedy distribution. And so again, the question is, how will I know? And the answer is, well, first of all, the density is complicated. The density is complicated because the Tweedy distribution is part of what's known as exponential dispersion models, and in their most general form have a very complicated PDF. But one of the applications of it is if you can imagine your data as coming from a Poisson number of independent and identically distributed gamma random variables, then you're in good shape. And so that, because of the influence of, say, Mr. Hewitt, and the fact that actuaries tend to think of the number of claims that any particular insured is going to have is Poisson, because they have nothing to do with, different insureds have nothing to do with one another and that sort of thing. They tend to think that the total dollars lost in any given policy is Tweedy distributed. The number of events coming in is Poisson, that's the number of claims, and the severity of each of those claims is gamma, according to the influence of Mr. Hewitt. And so when you put those two facts together and you sum up a Poisson number of gamma random variables, what you get is a special instance of the Tweedy distribution. And moreover, the Tweedy distribution is nice because it generalizes but most of the distributions we've seen before. Gamma is a special case of the Tweedy distribution. Poisson is a special case of the Tweedy distribution. This particular framework is a particular case of the Tweedy distribution. Normal is a particular case of the Tweedy distribution. And so in a certain sense, you can think of a lot of the work that's been done on all these distributions as coming from trying to parameterize a larger and larger number of probability distributions so that the work that we do can be more and more flexible. And so that's the answer on maximum likelihood. It's like, we have these parameters in our model. They have to come from somewhere. What do? I don't know. But I do know that if my conditional distribution is one of these 5, or there's other things in the software, is one of these 9, then we can employ maximum likelihood estimation to obtain estimates of those parameters. So that's that. We move on to the least squares method. Okay, and this is a very short slide. So it turns out that the conditional expectation has this fun little property, assuming that y has variance, which, come on, everything's got variance, has the property that the conditional expectation is the random variable that minimizes the squared difference between it and the original phenomenon. And so what I mean by that is if you take any other random variable z and you compare it to your target phenomenon, you look at the squared difference there, and you take the expected value of that, that will always exceed the expected value of the squared difference between your conditional expectation and your target phenomenon. So that's useful to know, because then what it says is, well, hey, whatever you're doing with your conditional expectation here, whatever needs to be estimated by it, we know it has to have this property. So you better start off minimizing the difference, the squared difference there between it and the target phenomenon. And that gives rise to minimization of squared errors. And that comes from the fact that the conditional expectation in linear algebraic terms is the projection of your target phenomenon onto the subspace spanned by the random variables x1 through xn. You look at the set of random variables that are measurable in the sigma algebra generated by x1 through xn. And so that's the reason why it does this. Projections generally minimize squared differences, and conditional expectation is a particular case of projection. And you say, geez, Ian, it really seems like not a lot of stuff is being assumed here, whereas a lot of stuff was being assumed in maximum likelihood estimation. Why don't I just use least squares all the time? And it's like, well, okay, that's a decent question. The answer is that if the distributional assumptions are met in the case of maximum likelihood estimation, the estimates that you get out of that have very nice properties. Although those are similar to properties that you get for estimates that come out of here if certain conditions are met. But that's the reason why. So at the very least, if you're doing a Bernoulli distribution, you know when your response is 0, 1, use maximum likelihood estimation. And that's the reason why, is because the properties of the parameter estimates are very nice. But, of course, we don't always know. So now we have to investigate what is the result of that. So here we go. We will go to our good friend, Mr. RStudio. Okay. So now we examine the consequences of our vast ignorance. So here we go. Load these guys up. We're going to generate a bunch of observations. And here's what we're going to do. We are going to look at normal random variables, Poisson, Gamma, Bernoulli, and Tweedy, and we're going to see what happens when we get it wrong. So here we go. Here's our data set, and now we're going to generate a normal random variable. So we use the rnorm function here, and we check our work. And we go, yep, those are the estimates we think. 1, 2, 3, 4. 1, 2, 3, 4. Okay, we're in good shape here. Now, it should be observed that gamma random variables only work on strictly positive target phenomena, so that's where their support is, and so we're going to restrict our attention when we're doing these GLMs to just the place where the normal variable came out as positive. So we create a normal model there, and now we're going to get it wrong. Okay, we're going to say, okay, whoops, we're going to create a Poisson model instead, and oh crud. All right, so it throws an error. Why does it throw an error? It throws an error because it says, hey, you haven't given me any starting values and I have no idea what to do here. Okay, so what's going on? Well, like we said last time when we were talking about optimization routines, that's from whence these parameter estimates come. That's why it's called maximum likelihood estimation. That's why it's called least squares, is we're trying to maximize things, we're trying to minimize things, which means there's an optimization routine involved, and optimization routines have to start somewhere. And if you don't tell it where to start internally, it's got its own subroutine which goes, okay, well, this jerk didn't tell me where to start, so I'm going to figure something out on my own. So in this case, what we're going to do is we are going to, because that subroutine failed, we're going to say, okay, Mr. Poisson model, why don't you start where the normal model ended? Like, we already have a set of parameter estimates that came from assuming normality. Why don't you start there instead? And so, boom. So it's doing its thing, and now you might say, well, gee whiz, Ian, you're giving the game away, aren't you? Like, you're just handing it the answer. Isn't that going to kind of bias the results? And the answer is, yeah, maybe, but we'll examine that, right? So again, we'll try to do a gamma. Again, it throws an error. It says, I don't know where to even start. We say, okay, start with the ones coming from the normal model. And boom, looks good. Tweety, again, no starting values. So we say, okay, use the ones coming from the normal model. It goes, okay. Now here's what I want you to see. Is that in this case, so recall, just again, in real life, again, assuming you're not doing Bernoulli stuff, you don't know what the conditional distribution is of your target variable with respect to your predictor variables. You don't know. And yet, if you want to make use of the software, you have to make a decision about what ridiculous assumption you're going to make. And so, a reasonable question is, well, what happens if I make the wrong assumption? Or is the project doomed? Does the space shuttle explode? The answer is, well, I don't know. Let's intentionally make those errors here, and then let's just look at the results. So we've now built 4 models, and look. What are the parameter estimates? Well, they're not the exact same, so that's a good first indication. If you were worried that, hey, if we're just handing the Poisson or Gamma or Tweety models a starting point, aren't they just going to pick the starting point? You're kind of cheating here. And the answer is no, they actually do move away from the starting point, because their starting point for all 3 of those was these guys here, and they all landed someplace different. So we weren't really biasing the answer, we were just helping them out. And so, yeah, they come up with different answers. Not surprising, because they're maximizing different things. However, it's not like they're completely different from one another. These are all close to 1, these are close to 2, these are close to 3, and so on. Moreover, and I would say most importantly, let's look at the correlations between them. And there you go. The correlations are at nearly 1. And so what this means is, if you generate a normal random variable, and then you deliberately use a different distribution, Poisson, Gamma, Tweety, it doesn't matter. It makes no material difference. Yeah, your estimates are different, duh, but they're not crazy different. They're not changing signs. It's not like one is saying positive, the other is saying negative. They're all pointing in roughly the same direction with roughly the same magnitude, and the outcome is the same. They're correlated at near 1. Okay, so why did those models fail when we tried them initially? And the answer is because internally, the way these things are programmed, the Poisson programming, for the most part, assumes that you're going to use you're going to have a multiplicative model. Whereas in our case, we elected to use an identity. We did not transform our linear combination of things. Similarly with the gamma, it's kind of thinking that you're going to do you're going to exponentiate stuff. Same thing with the Tweety, but we didn't. And so it kind of didn't know what to do with itself, so we had to help it out. Why does this matter in practice? Well, it matters in practice because suppose that you do not want a multiplicative Poisson model. Suppose you want an additive one. What that means is that you are going to have to make use of an identity link function. But if you're making use of an identity link function, it might throw an error because it doesn't know where to start, in which case you first create a normal model using an identity link function. That gives you a better set of estimates from which to start, and then you feed that into the Poisson one, and now everybody's happy. Okay, and now the rest of this code is just doing the exact same thing like 4 more times. And so here we go. We create now a Poisson random variable. We go, yep, okay, 0, 1, 2, 3, 4. Okay, it's doing what we want it to do. But now we find ourselves in a very happy predicament, and the very happy place in which we find ourselves is that all of these models have just run. None of them threw errors. Why is that good? Well, it's good because this normal model, we did not provide it with initial values. This one, we did. And so now what we can do is we can get a sense of the impact of how it might bias the results if we say to the normal model, hey, why don't you just use what the Poisson model came back with? It'll be our little secret. And same thing for gamma and same thing for Tweety. Now we can actually look at the output of that, the outcome of that, and lo and behold, whether or not we seeded the normal process with the parameter estimates coming from the Poisson model, it didn't make a difference. they're next to identical to each other. I guess here we're different at the 8th decimal place. It didn't make any difference. And so that should hearten us that even if we do end up using the results of one regression distributional assumption to seed to another regression with a different distributional assumption, we're not just giving the game away. Similarly here for gamma, again, it's picking them up 1, 2, 3, 4. Again, they're next to identical. Same thing here for the Tweety random variable. It's getting the parameter estimates 1, 2, 3, 4. And again, they're pretty much the same. So we should be heartened by that. And again, you say to yourself, okay, well, what's the material difference between them? The answer is there isn't one. Even though we are deliberately making mistakes, we're creating a Poisson model, a Poisson random variable, but then we're modeling it with normal and gamma and Tweety. It doesn't matter. Okay, now we're going to do the same thing with gamma that we just did with Poisson. Again, everything's going to be brilliant and run nicely. And we get to, again, take a look at the material difference between whether or not we give starting values to the regression. And let's take a look. And again, the parameter estimates coming out of normal are what they should be, 1, 2, 3, 4. And whether or not we seeded them with the true parameters coming from the gamma regression didn't really make a difference in any material way. Same thing for the Poisson. Same thing for the Tweety. And once more, look, boom, correlation, near 1. So we are deliberately violating our distributional assumption. It makes 0 difference with respect to the conditional expectation. Now we're going to do Bernoulli. This one's going to be a little bit easier. So the thing about Bernoulli is that because it takes only 0 and 1 values, again, you know it's Bernoulli, but the other thing is that only the normal and the Poisson apply to this, because I suppose we could also do it with a Tweety, but we'll only do it with normal Poisson. Gamma doesn't apply because gamma assumes that things are bigger than 0, and so if you have something that gives you only 0 and 1s left, well, if you exclude the 0s, then all you have is the 1s. It's not an interesting model. But we'll deliberately be stupid again, and we'll try to model this with a normal. Oh no, it throws an error. Fine, we'll make it start with the Bernoulli. Oh, look at that! So we can in fact make a normal distributional assumption. Same thing with the Poisson. It's going to throw an error, but when we seed it with the ones coming from the Bernoulli regression, we will be in good shape. And then once that runs, it appears to be taking its time. Come on, you. We can compare the coefficients here. And again, now in this case, we alternated the signs on the coefficients because if you made them 1, 2, 3, and 4, then you would get pretty much all 1s back. So we mixed them up. But again, look, the normal coefficients come back the same way as the Poisson coefficients, 1, -2, 3, and -4. So look, it's figuring out where it needs to go. Everybody's roughly in agreement, even though we blatantly violated the distribution assumptions. And the correlation, boom, it's at, again, it's nearly identical. And finally, we'll do this with a Tweety model. And here we go with that. So we're going to run all of those. And it's going to be the same old stuff. We should get back 1, 2, 3, 4 as all of our parameter estimates. And then we can go through and we can compare what comes out of them, and lo and behold, again, it doesn't really matter whether or not we are seeding the optimization routine with the true estimates coming out of the true distribution. We're getting the same numbers back. You can see that right there. We're getting the same numbers back. And again, we are getting correlations at next to 1. So we should be heartened by all of this, because what it means is that we are able to we are able to explicitly violate distributional assumptions, and yet it doesn't seem to have any impact on the final answers that we're getting from these things. The parameter estimates are roughly the same in all cases. The predictions are nearly identical in all cases. And so that should give us hope that when we are doing this work out in the field, where of course we have no idea what the conditional distribution of our target phenomenon is with respect to our predictor variables, that's okay. We're not everything's going to be fine. The spaceship is not going to explode. We really can rest to a certain extent on the estimates that we get back. Now, theoretically, why should this be true? And the answer is it goes back to what we saw in the PowerPoint presentation, which is that the minimization of the sum of squared errors, that always holds. It holds no matter what the conditional distribution of y with respect to x is. That statement is always true, independent of the conditional expectation. And so that's the theoretical reason to believe that ultimately, at least with respect to the conditional distribution, all roads lead to Rome. That we eventually get to the same answer in all cases. My theoretical conjecture with respect to maximum likelihood estimation is that it is akin to something in functional analysis called equivalent norms, or if you do metrics-based work in real analysis, equivalent metrics. That is to say, different measures of distance, which nonetheless produce the same topologies or open sets, the same convergent sequences. And so my conjecture is that these maximum likelihoods, these likelihood functions that we're maximizing, that those answers are in some ways equivalent to one another in some heretofore unstated fashion. It is, of course, only a conjecture. Finally, it should be observed that this work that we've done, making a big deal about the fact that with respect to the conditional expectation, it doesn't matter what your distributional assumption is, that has to do with the conditional expectation. If you want to sample from a distribution, it makes a big difference what your distributional assumption is, because in that case, that's the whole point of the distribution, is you want to sample from this distribution and not that distribution. That's the whole point of it. But if all you care about is the conditional expectation, then it doesn't really seem to make that big of a difference. And instead, although this seems a little wacky, the real way you should select your distribution is it should cohere with the programming of the link function you intend to use. So we already saw that if your link function is an identity function, gamma and Poisson and Tweedy get real bent out of shape real fast. And similarly, if your link function is a logit, normal and Poisson get kind of angry pretty quickly. And so you should first consider the form of the conditional expectation that you want, select your distribution accordingly, get your parameter estimates, and then worry about if you want to tweak what your conditional distribution assumption is going to be. When you find yourself in the case where you have to do some sort of sampling, and that is to say in a case where you do care about the distribution of your target phenomena, then your best bet is simply going to be to, one, build your conditional distribution, build your conditional expectation, and then with that in hand, what you can do is you can try all of the different distributions that are programmed into your software, and just use the Kolmogorov-Smirnov test on it, and just pick the one that most closely matches the your data, and that's going to be your answer. Is it the right answer? Of course not. There's as many distributions as there are sequences of non-negative numbers that add to 1, and that's way too many to program. However, you still have to make a decision at the end of the day. That means you have to use the tools that you have, which means that unless you want to take the time to program an ever more increasingly flexible sequence of distributions, you work with what you got, which means that you estimate your conditional expectation, you try that in all the distributions in the software, you pick the one that is the best fit, you sample with that, and you move on with your life. I hope you found this presentation to be useful. If you have any questions, please leave them in the comments.